Hello, it's Stat 134, Lecture 36. Last time we were talking about the conditional density, and we're going to continue doing that for a little while. The average conditional probabilities can come in different varieties. You could have x discrete, y discrete, x continuous, y continuous, x discrete, y continuous, or x continuous, y discrete. And we have different formulas for the average conditioning probabilities. So I asked you guys to find it for x discrete, y continuous, and x continuous, y discrete. If x is discrete, then instead of an integral, you have a sum and a probability mass function. Y continuous, in that case, we have y and dy. And if x is continuous, then we have an integral and a density. And y discrete, we have y equals y. So today we're going to do some more practice in section 6.3, and then we'll start section 6.4 on covariance and variance of the sum. So I asked you guys this question. Suppose that y is Poisson x, where x is exponential lambda. Show that the unconditional distribution of y is geometric lambda over lambda plus 1 on 0, 1, 2. So you can recall that z is geometric p on 0, 1, 2, and so on. If the probability that z is k is q to the kp, so we need to show that the probability that z is k is 1 over lambda plus 1 to the k times lambda over lambda plus 1. So we have y discrete, x continuous, so we have the average conditional formula shown here. We plug in for the conditional probability and the density, and then this is the tricky step here. You can recognize a gamma here, and if you rearrange things a bit, you can make this integral 1, in which case we'll just have lambda over lambda plus 1 to the y plus 1 power. And this we can rewrite as 1 over lambda plus 1 to the yth power times 1 over lambda plus 1, which is essentially what we need. So that shows that y is geometric lambda over lambda plus 1. As a follow-up question, show that y equals k, the conditional distribution of y of x is a gamma distribution, and provide parameters. Okay, so we're looking for the probability that x is in dx given y is k. So this is the area of the conditional density. This is the area of the conditional density, which we can approximate as the conditional density at x times dx. And we can use Bayes' rule to write this as the joint over probability that y is k. And then the multiplication rule for the joint is probability y is k given x is x, fx is x, dx, over probability y is k. And then we just plug everything in, and we see the variable part of this is x to the k e to the minus lambda plus 1 x. And so we conclude that x is gamma k plus 1 lambda plus 1. So we're done with section 6.3, on to section 6.4 on covariance and variance of a sum. So we have x, y, s is x plus y, the mean of x mu x, the mean of y mu y, the mean of s mu s. The variance of s is the expectation of s minus mu s squared. That's just the definition of variance. ds is the deviation from the mean. And so ds is s minus mu s, which you can also write as dx plus dy. So the variance of S is the expectation of dx plus dy quantity squared. If you FOIL that and you distribute the expectation, we get the variance of x plus the variance of y plus 2 times expectation of dx dy. And that new cross term is what we call the covariance. So expectation of dx dy is the definition of the covariance of x and y. So there are certain bilinearity properties. We have the covariance of x plus y z is covariance of xz plus covariance of yz. The covariance of ax by is ab covariance xy. And more generally, the covariance of a sum of ai xi sum bj yj is just this big double sum ai bj and then all the mixed covariance terms. So this is proved at the end of the lecture in the appendix, and it's very straightforward. Another thing proved at the end of the lecture is the covariance of xy is expectation of xy minus expectation of x expectation of y. And here this makes sense because if y is equal to x, we just get that alternate formula for the variance of x being the expectation of x squared minus expectation of x quantity squared. And some easy other facts: covariance of x is variance of x, covariance of xy is the same as covariance of yx, and that's because in the definition of covariance, well actually I guess you can just see it right here. If covariance xy is expectation of xy minus expectation of x expectation of y, this is symmetric in x and y. Furthermore, the covariance of xc is 0. That makes sense because if you let x be c, then this would say the variance of a constant is 0. Great. So I asked you guys to apply these rules to simplify this complicated covariance. And so you have x, 3x, so the 3 pulls out, so you have 3 variance x, and then you have x, y, so that's covariance xy, and then you have x minus z, so the minus pulls out, covariance xy. Then you have x, 10, that's 0 since 10 is a constant. Then you have minus 5y, 3x, the minus 5 times 3 pull out, covariance xy. And then we have minus 5y, y, so that's minus 5 variance of y. Then you have minus 5y minus z, so minus is plus 5 covariance x, y, z. And then finally covariance minus 5y 10 is 0. So then let's recall that if xy are independent, expectation of xy is expectation of x expectation of y. So now covariance of xy is that second definition that we had earlier. Let me see if I still have it here. Yeah, this theorem here says that the covariance of xy is expectation of xy minus expectation of x expectation of y. So if those two terms are equal, then the covariance of xy is 0. So when xy are independent, the covariance is 0. So if x and y are independent, the variance of x plus y is the variance of x plus the variance of y, because the covariance term is 0. So we then did a concept test. So we have a Poisson process. TR is gamma r lambda, the rth arrival time. The covariance of T1, T3 is. So T1, T3 is are dependent, but the trick here is that T1, T3 minus T1 are independent. So the covariance of that will be 0, and then by the bilinear properties, we have the covariance of T1, T3 minus the variance of T1 is 0, and then solving for that, we have the variance of T1 is 1 over lambda squared using the formula above. So we have the covariance of T1, T3 is 1 over lambda squared, so it's C. Furthermore, if x1 to xn are identically distributed and you look at the variance of the sum, this is a covariance of a sum of these xi's, sum of these xi's, and all the xi's are identically distributed. So we're going to get n squared terms, and those n squared terms appear in this variance covariance matrix. And the diagonal elements of this variance covariance matrix are variances, and the off diagonals are true covariances. And so we can write this as n times the variance of x1 because all the variances are the same, and n minus 1 covariance x1, x2 because all the off diagonal true covariances are the same. So now an application of this, imagine that you have a box with x1 to x capital N, having population mean mu, population SD sigma. We draw n without replacement. This is called a simple random sample. So x1 to xn. So Sn is the sum x1 to xn. That's the sample sum. And so we're going to find the expectation of Sn and the variance of Sn. The expectation of Sn is just n mu. That's pretty obvious. But the variance of Sn, we're going to use our formula there. So it's n times sigma squared plus n minus 1 covariance x1, x2. So we need to find covariance x1, x2. And here we use a trick. So we're going to take a census. So we're going to let little n be capital N, just temporarily. In that case, our sum is all of the sum of all the tickets in the box, and that is always going to be the same. So the variance of that is 0. So we have 0 is n sigma squared plus n times n minus 1 covariance x1, x2, and you can just solve for covariance x1, x2 to get minus sigma squared over n minus 1. So now that we know what the covariance of x1 and x2 are, we have a formula now for the variance of S sub n, and that's n sigma squared plus n minus 1, then minus sigma squared capital N minus 1. Do some rearrangements here. We get n sigma squared times n minus little n over big N minus 1. And you'll recognize this as the correction factor. Capital N minus little n over capital N minus 1 is the correction factor that you get for doing sampling with without replacement instead of sampling with replacement. If you had sampled with replacement, your variance of Sn would have just been n sigma squared. But because you sampled without replacement, we have this correction factor. And we've seen this before. So for example, for binomial, which is a sum of n independent trials, the variance of x is npq. Now, if x is hypergeometric, n capital G, you can think of that as you're drawing from a box, population size capital N. You're drawing n without replacement, and there are capital G good tickets and n minus capital G bad tickets. And then the variance of x will be npq, which is p is g over n and q is capital N minus g over n. And then we have this correction factor, which is for drawing without replacement. Remember that in the hypergeometric, all of the trials are dependent on one another. So next time we'll do correlation, and have a great day.